Yeah. Okay. So we have a polynomial p, and sort of for computer implementations, we will think of polynomials as lists of coefficients, and then sort of the first entry in our list will be the constant coefficient, the last will be sort of the highest monomial, and we can split it up in the following way. We have sort of the coefficients of even degree, so it starts with the constant part a0, then comes to a2. So this is the square part, right? And the same with the odd part. So if we want to get our original p back, we have to plug in x squared, raise everything to like double all the exponents here, and then for the odd part, get one more x. Yeah, I guess. And then if you want to multiply two polynomials, you can do this in a slightly clever way. Well, you write both polynomials like this, and then instead of like multiplying this, and then all the combinations, you get the even part, you get the odd part, and here's sort of the mixed part, where you do it in a clever way where you sort of add even and odd for each of them, and then subtract those two guys that appear here and here. So maybe you can see that, yeah, this is actually just a product. You shuffle things around, but now these two guys appear twice, so you only have to apply this weird sum. So if you look at this as a polynomial, it looks maybe a bit weird. So if we write an algorithm function Karatsuba, it takes polynomials of p and q as input, and then we have to be a bit careful if one of them is constant or is 0, I guess. Then we just do like normal scalar multiplication with that, because if we have a constant polynomial, we can't make it smaller by splitting in even and odd part, right? The even part will just be the original thing. Otherwise, we compute these three guys recursively and then return this expression. And the trick here is, because we only have 3 recursive calls with this with some product, we have an algorithm that runs asymptotically faster. So, okay, if we want to implement this in our favorite proof assistant, we have one problem, namely that determination checker. If you want to write this algorithm in Agda, then the determination checker will tell you that you can't tell that PE and PO are structurally smaller than the polynomial we start with. And an easy way to get around this is by adding so-called fuel. So you add one more input to your function, and you basically natural number that reaches 0. You just do the slow multiplication, sort of. If it's performed successful or something, you decrease by 1 in all the recursive calls, and otherwise the algorithm. And yeah, this is, for example, the solution they took in the EAL library. That's the paper I referenced here. And then, so for actually getting a function that just takes 2 polynomials, you plug in a natural number, and yeah, you take the length of the list of coefficients or the degree of the polynomials, and the idea is that, well, I'm going to say this in a bit, but there's also maybe other ways to deal with this general problem, but today we're going to work in this setting. So yeah, the idea is that the maximum of the degrees of the polynomials, if you sort of in each recursive step only decrease that by 1, you'll be done with the algorithm before that reaches 0. So you never reach the case of slow multiplication. But this is something that you only think about externally. That's not something you put in the Agda, because I think it's much more complicated. And yeah, so when we say we want to prove this algorithm correct, we want to say, well, for any n, this is just multiplication, and then we pick something that externally know is bigger than the number of recursions we have to do. But there's another, well, okay, how do we put this? Well, induction on n, base case, we'll just define it to be multiplication, so that's for free. And then the inductive step, that's modular using the hypothesis, that's just showing this algebraic identity that we just rewrote the product in a clever way. But here's a problem. If we just take polynomials to be a list of coefficients, then sort of the type of lists over a ring, that's not a ring itself, right? So showing an algebraic identity is kind of nasty. And well, you might say, well, just power through, right? So maybe the most direct solution is that, well, we actually proved this algorithm correct for list inputs. So we had a bachelor student doing that, and he didn't finish. It was very painful. I feel a bit bad for making him do it. The better approach is to take an implementation of polynomials that actually are polynomials that carry ring structure. But usually you have to assume decidable equality on the base ring. And then you can, for example, present polynomials by lists where the last entry is non-zero, right? This will be the degree of your polynomial. But then, yeah, imagine if you add two polynomials together, and you add the coefficients bit by bit, you sort of then have to go through the whole list and decide where the last non-zero entry is to get it back into normal form. That's why you need decidable equality. And what I want to do today is sort of use high inductive type for representing polynomials that gets us in the best of both worlds, so that we can get a ring structure to prove this algebraic identity very easily, but do not have to assume decidable equality. And I'll put a link to the pull request if you want to look at that. So yeah, the idea is that polynomials are lists of coefficients, but sort of if you add zeros in the end, you still stick with the same polynomial, right? So it's a very simple hit. You first have your list constructors. Empty list is a zero polynomial. You have the cons, which adds coefficients, and then you have one higher constructor, and then this tells you this is sort of the constant polynomial number zero. It's just the zero polynomial, and it turns out that's all you need to sort of get a one correspondence with polynomials up to half. So you can prove, even without assuming that R has decidable equality, that this has a commutative ring structure. We also had another bachelor student do this, and it's actually the right ring structure, right? It has the universal property. You want to check that, so you know you have done polynomials, not something else. Okay, so yeah, now we want to do Karatsuba for this high inductive type, and this is sort of the type signature of the basic algorithm with fuel. This is the type signature of the correctness proof that we want to carry out. But because we have this higher constructor drop zero in Rx, we sort of write this as a mutually recursive function, where we sort of use the correctness proof to fill in the holes when we define the algorithm for the drop zero cases. And well, first, the non-higher cases are just as you expected. When you reach zero, it's just multiplication. Then sort of those four cases are dealing with the cases where, I don't know, multiply with zero or a constant. And this is sort of, both of them have at least two elements, and then you do the recursive algorithm. But then you have the higher part. It might be a bit small to read. I couldn't fit it otherwise. And then if you program cubical algebra, you know, things get yellow very quickly when you have higher constructors. And actually, I mean, I don't want to go into detail what this is, but this is very hard to prove or to fill if you don't sort of assume that you already have the correctly working algorithm in the other cases. And then we of course have to do the main correctness proof, but because that goal is a proposition or an H proposition, that's really just doing the algebraic manipulations that are at the heart of the correctness argument. And so yeah, we want to follow the general strategy. We given P and Q. We want to say Karatsuba algorithm on P and Q is this fuel algorithm where we pick the fuel big enough, and the fuel can of course depend on P and Q. But here's the problem: we don't have the length of our list of coefficients anymore, right? Because of drop zero, sort of any list that just has zeros in it will be equated up to path. right? So they all have to be assigned the same value if you want to write a function into natural numbers that splits up the length. And well, one solution to that would be, of course, assume decidable equality, and then we can define the degree, but yeah, that's what we don't want to do. So we can't do the degree either. Here's what we can do. We can write a function into the proposition truncation of the natural numbers. So on the empty polynomial, this will just be the point constructor of 0. And then if this is of the form of a const constructor, then we use map. So proposition truncation is a monad, right? So we map the successive function on whatever we got on P. And so the drop 0 has to be a path between 1 and 0, but everything is equal up to path in the proposition truncation. So that's for free. And yeah, maybe you want to figure out for yourself that if your polynomial is actually just a list of coefficients and you don't have any drop 0 popping up anywhere, then you really get just the length of this list sort of in the absolute value brackets of the proposition truncation constructor. And then, okay, how can we use it? So the computational information is still there somehow, but everything is equated up to path. So how can we use that? So here's this lemma that you're hopefully aware of. If you so if you have a function from type A into an H set B, all you need is proof of weak constancy. So for any x and y and a, the path from f of x to f of y, to construct a function out of the proposition truncation by A into B that computes definitionally just to f on the point constructors. And yeah, that's what we have in our case. So we want to define a binary operation, right? But that's a set because rings are taking the sets in our setting. And we just prove that for any n, our Karatsuba rect is just multiplication. So those are equal as functions by functional extensionality, I should say. And so we can factor through it's up here, so you can't really see it. Factor through the map that goes from n into the truncation of n. And we get this function Karatsuba trunk rect. And then, oh yeah, exercise. There's also another way of doing this where you use that singletons are contractible. So you look at the singleton of multiplication in the type of binary operations on your polynomial ring, and then you observe that Karatsuba rect for any n lands in this singleton, and yeah, you can use this to get another function of this type. So yeah, maybe you can try to spell that out. And then it's also interesting to think about how the computational behavior of those two functions compares. And well, yeah, now we're kind of done because we take our P and Q, we take our fuel that will be basically the maximum of length, but modulo dealing with the proposition truncation, and we plug that into our algorithm with the truncation of natural numbers. And more exercises or sanity checks. If P and Q are actually just lists of coefficients and no drop 0 anywhere, then yeah, then it really should just be the original algorithm that I showed you in the very beginning. So yeah. If you're very familiar with how truncation works and stuff, then you might see it directly. And then of course something that I didn't say anything about is that, well, we did a bunch of tricky stuff, but maybe it's worth convincing ourselves that Karatsuba still is just multiplication as a function, even without the trickery with the truncation. But yeah, I'm gonna leave that as for the interested people in the audience. So I want to end with maybe like a general recap of what I've done here. And then hopefully maybe you have some ideas for similar algorithms where similar techniques could be applied. So you start with you have your favorite algorithm and you want to implement a provably correct version in your favorite proof assistant. You might have to add some fuel to make the termination checker happy. But in any case, we sort of are in the situation where giving some like either fuel or maybe something else that depends on how your input data is implemented, and that might not be a one-to-one correspondence with sort of data that is represented by your implementation. And the next thing is that maybe you also have a hit for your input data, and that should make the correctness proof easier, but it sort of breaks the algorithm because all of a sudden you get a conflict here. Well, in our case, there was always the exception of decidable equality, then everything would still work, but like in the general case, that's what happened. But yeah, there's this nice trick about factoring through a map that truncates naturals, and we can program with our hits and prove our algorithms correct quite conveniently. And yeah, I mean, now this is just a pull request to the cubical algebra library. I want to make this into an executable program, and this you can do now with the raised cubical flag. So you can compile cubical code almost into runnable programs. And I'll be very happy if you guys have ideas for other algorithms where similar tricks could be used. Yeah, that's all. Thank you.
One question, yes, time for questions.
Hi, I was so maybe just one other thought of something you could try as in like either instead or in addition to is instead of trying to define a function from your hit to length, is it possible instead to sort of define a proposition to say the length of this is bounded by something? And I wonder if that would give you a bit more flexibility. It probably ends up with the same problems that you have to at some point define this function from to the natural numbers. I'm just wondering if phrasing it in a slightly different way and allowing things to have multiple different lengths might somehow make stuff easier.
Yeah, I mean, another way of dealing with the problem with the termination check is not introduce fuel, but some sort of predicate on polynomials saying one polynomial is less than the other if the degree is smaller or the length of the representation is smaller, right? And then you do induction on this. It will find the induction to prove your algorithm correct. But then again, like in the hit case, you run into problems with defining this because I think there are a bunch of possible ways to deal with it, but it all boils down to the naive length is not
Yep. Okay, then should proceed with the next talk. Thank you.